All right, welcome back. This is the end of Lecture 4D, Modeling Observed Polytomous Data. This is the lecture we started on Tuesday, November 5th. We didn't quite get all the way through, so we're going to start up where we left off with the multinomial models. We talked about kind of the generalized sense, generalized models and how they worked, but now it's time for us to start into the categorical or multinomial distribution models. So we talked about the last time the binomial model did not quite do what we wanted it to because it didn't have an asymmetric type of distribution. It wasn't multimodal. Those problems are remedied in the multinomial or categorical distribution models. Last time we talked about the multinomial distribution. It is a generalization of the binomial. So you can think of the binomial distribution that we saw last time. We had a number of successes out of a number of trials. Now, you think about each trial has two options, a success or a failure. So when we talk about number of successes, we also know the number of failures. Here, for a given trial, we have a probability of capital C different categories or categorical outcomes happening. Each of those has a different probability, and the sum of those probabilities sum to 1. So this likelihood function has a product of the probabilities, but it's raised to the power of how many times that outcome was observed in n different trials. Now, if you only have one trial, this is sometimes called the categorical distribution, and the likelihood function simplifies, where the normalizing constant disappears, and everything that you see here happens to be the probability for each class or each outcome category raised to the power of an indicator function if that category was observed. This raises the probability to a 1. If it wasn't observed, raises it to a 0, making it go to 1. So psychometric models that use this distribution end up having a set of what we call submodels. Submodels basically take the probability that's estimated, right? So here, all but the last probability, and put a model onto that, the psychometric model itself. So the different types of models that we have for polytomous data in item response theory, typically where this is described, or item factor analysis, differ in how the model function builds the conditional response probabilities. For instance, the graded response models provide a set of ordered intercepts or thresholds and a single loading. So what happens is, if we take our example where we have 5 options for each item, there'll be 4 submodels. Each submodel has its own intercept, but all the submodels share the loading parameter or discrimination parameter. Sometimes this is called a proportional odds model in categorical data analysis because the odds of any category increase proportionally across because of the single discrimination loading parameter. Partial credit models are another type of psychometric model. Now, these often are developed in educational measurement. They provide a set of unordered difficulty parameters in a single loading. So you can see certain categories sort of switch probability, whereas the graded response model, because of these ordered intercepts, the probabilities are sort of somewhat ordered as well with it. And finally, there's a set of models called the nominal response models, where each submodel has a set of intercepts that are unordered, and each submodel also has a set of loadings that are also unordered. And we call this a generalized logit model in categorical data analysis. Now, the note that I really want to make about terminology is that terms graded response model and partial credit model come from educational measurement. The data that you have don't necessarily have to be item responses on a cognitive test where partial credit or graded response might be given. We just need data that follow this idea where ordinal categories exist in the data. And that's our data, right? We have a Likert scale. The first option is strongly disagree. The second option is slightly disagree. And you can see as the option number increases, we have this sort of idea that increasingly, as a person's trait increases, they're more likely to pick a more agreeable option. So that really provides the ordering that we see in the data that we have. So the graded response model itself, the submodels, remember, this is the submodel. This is the probability that an observed item response is equal to category C, right? Well, that is the difference between the probability the item response is greater than or equal to the previous category, minus the item response being greater than or equal to the current category. So it's sort of a difference model between adjacent categories. And this cumulative P star function, the item response that is the probability that y is greater than or equal to a given category, that thing is where we put our psychometric model. So here in the psychometric model, we see our single lambda and our single theta. This is a unidimensional example here. And we also see mu I, but now there's a second subscript, mu IC, representing it's that submodel C's intercept. Now the mu's themselves are ordered. So the first submodel's mu is less than, or greater than, the second, and so forth. And to make the math work out in this range, we have two other constraints. The probability of being in the first category or higher is equal to 1. Well, that makes sense because you can't be below the first category. And 2, the probability of being in a category above the highest category is equal to 0. So in that case, this math works out for all categories. So how we code this in Stan is actually quite convenient. Stan has an ordered logistic function that takes the categorical distribution, or the one-trial multinomial, and provides for a series of ordered logistic responses. Here, the function ordered logistic indicates that y should be an integer, but it should have ordered categories starting with the number 1 and going up to some maximum number of categories. Then, the ordered logistic function takes two arguments, the first being the part of the linear predictor that's not the intercept. And I'll say intercept for now, but technically it's threshold, and I'll mention that in just a moment. So this is lambda, the factor loading or discrimination for that item, times theta. And the second argument is the set of thresholds for the item. Now, thresholds turn out to be -1 times the intercept. So the parameterization that I showed you on this slide, we have to replace mu IC with negative tau IC, which also changes the direction of the inequality as well. But this is all taken care of for us in Stan. We don't have to do any additional coding to make this work. Let's see, next. The thresholds themselves, because there are 4 per item in our example now, show up with their prior distribution in the loop. Because each item, with having 4 thresholds, we can use that multivariate normal distribution to describe the prior distribution for these. But because each item has 4, each item essentially has its own multivariate normal distribution. And again, in a multivariate normal distribution, the mean vector and the covariance matrix are the hyperparameters. And we can make it so that each item has its own unique mean vector and unique covariance matrix for the hyperparameters. And we'll see that in the next slide. But one thing I will note is that this mean vector right here is actually yet now an array also. And this covariance matrix is actually a 3-dimensional array. We're going to talk about that in the next slide. The next two priors, theta being standard normal and lambda following a multivariate normal with some imported mean vector or covariance matrix for hyperparameters, these are the same we saw in the other models up to this point as well. All right, let's move on. The greater response model parameters block is where we start to see a few differences. Now, theta and lambda are the same as you've seen before, but for the thresholds, this is an array now. Remember, each item has 4 thresholds. So we have the number of items as our first dimension of our array. And in the array statement in Stan, we have to declare the type of variable that shows up in the array. Here, we're going to use a special data type in Stan called ordered. This is another convenient feature of Stan. It ensures basically that these thresholds follow the order that you see here, such that the first threshold is less than the second, and so forth. This is critically important for the graded response model to function. Now, the fact that ordered shows up means that for each item now we have maximum number of categories -1. So in our case, 5 categories -1, or 4 ordered thresholds for each item. That's what's happening. Now, in the generated quantities block, we can go transform our threshold into our intercept parameter, since I've been using that notation throughout class. This intercept parameter is just -1 times the threshold, and then we can output them intercepts and see how those look. Now, in the data part, things are a bit different as well, too. First, I'm importing the number of the maximum category. Now, you'll note here, I don't actually offset this by item, and I probably could, But I didn't because this helps us make an easy sense of an array right here. But this maximum category is the same for all of our items, and that happens to be number 5. Next, y is an integer array, like we saw with anything with Bernoulli or other types of binomial data. The items come first, the observation comes second. So this is sort of the transpose of our data matrix. And you'll note here I ensured that the responses that we see in y are between 1 and 5, which is our Likert scale that we've been using. Next, we see an array of, for the mean vector, these are the hyperparameters for the mean vector. This is described almost similarly to how we describe the parameter statement itself. It's an array where the first index is the number of items. Now, we say that the imported value that we're going to bring in is a vector with a number of rows or a number of columns, max category minus 1. So this turns out to be a 2-dimensional array where the first dimension is items, the second dimension is 4 for our example, or 10 and 4. For the covariance matrix for those thresholds, a similar thing happens. Remember, this is a 3-dimensional array because each item has its own 4x4 covariance matrix. So similarly, we define an array of n items, in our case 10, and we declare the type of variable to be a matrix. And that matrix has size 4 by 4, for example, or max category minus 1 by max category minus 1. This allows each item to have its own unique set of hyperparameters if we need to use them for the covariance matrix of the thresholds. And I cannot emphasize enough, if you have a small number of observations in any one category, you may need to make more informative priors on these thresholds. And this is the method by which you do so in this covariance matrix here for each item. Finally, the imported values for lambda happen to be the same as well as we've seen before. So I'll move on. Let's talk about how we build the data from R for the threshold parameter. Remember, the mean hyperparameter was a 2-dimensional array, which means we can use an R matrix for that. And I'll walk through the steps in my code here. So I want the mean hyperparameter for each item, for each threshold of each item, for all 4 thresholds to be 0. Now you may think that's a little weird. Of course, I had to do that. May think this is a little bit weird because the thresholds are ordered, they all shouldn't be at 0, but I like 0 as a number. Mainly, I'm going to make this a very uninformative distribution. So 0 being, it's not going to really make a big difference between 0 or some other value. So what I do with that is I remember that there are 4 hyperparameters for each item. So then I create a threshold mean vector hyperparameter vector where I take the 0 and I set it into 4 spots. That's what this rep function does. It basically returns 4 zeros as a vector. Then I initialize an empty matrix, and I go through each item, and I add each row of zeros for my hyperparameters to this matrix. So threshold THR mean matrix is the matrix that we will use for the hyperparameters for the thresholds, the mean vector of the thresholds. Okay, second, for the covariance matrix. Now, again, this is a 3-dimensional array, but let's walk through the steps in the R syntax here. I would like the diagonal of my covariance matrix to have a value of 1,000. This is, remember, the variance of the threshold parameter is what this represents. So it's a very uninformative number. So what I do is I create a diagonal matrix where the diagonal is 1,000, and this is a 4x4 matrix. So 4x4, the diagonal has 1,000 in each 4th spot, and then the off diagonal, every element is equal to 0. So now there's an R array data type. The array data type can be an object that has more than just 2 dimensions. Remember, a matrix just has 2 dimensions. So here I'm going to define the array to have number of items as its first dimension. And then if you think about that, once we have an item, the next 2 dimensions represents the size of this covariance matrix. So it's max category minus 1 by max category minus 1. Okay, so then finally, for each item, in that each first element spot, I put item through this loop, and I define it to be this covariance matrix. So at the end of all of this, the THR cov array is a 3-dimensional array. If you think of what that contains, each item then has a 2x2 or a 4x4 covariance matrix. That's what it's trying to show. All right, how do I call this in Stan? Well, similar to all the other times we've done this before, I'm going to initialize theta to its standardized sum score, initialize lambda to a very positive number. This is to help with convergence to multiple modes of the posterior. I run the model. I can see I had convergence, which is excellent. And here's the set of parameters I have. I have 10 loading or discrimination parameters. Again, now these represent something a little bit different. Remember, each submodel has its own lambda times theta. This is the increase in the submodel's logit for every unit increase in theta. And then if you look at the intercepts, you'll see mu11 represents the first element of this, represents the first item, and the second element represents the first intercept. So mu11 is 1.49. And mu12 is less than 1.49, or negative 0.655. Mu13, item 1's third threshold estimate intercept estimate was negative 2.51, and the fourth one happened to be negative 4.52. You can see these are in order decreasing as we wanted them to do. And how we interpret these is the following. Remember, intercept, if we go back to our submodel here, the intercept right here represents the log odds when theta equals 0. Right? So this is the log odds of the probability that y is greater than that category, greater than or equal to that category. So if we want to think about what this means, mu of 1.49, this means that when theta equals 0, or for an average theta, we would expect the log odds of a probability of being in category 1 or greater, actually in this case category 2 or greater, of 1.49. That 1.49 is on the positive side of 0, so that would be a fairly large probability. Okay, next. If we really want to describe an item, we can take a look at the option characteristic curve. This is something we showed for the binomial model. We can show it for the grid response model also. Here on the x-axis we have theta. On the y-axis we have the probability of selecting a category y conditional on theta. Right? And so if you want to think about what's happening, if you take a line straight up from any point of theta, the sum of where each of these option characteristic curves happens to be on the y-axis equals 1. That sum, they all sum to 1 for any given value of theta. Right? This is the grid response model itself, summing to 1 for the probabilities. But the way that we interpret this is the way we interpreted the same plot for the binomial. Here we can see that the option 1, which in our case was strongly disagree, was chosen by, most likely going to be chosen by everybody with a theta below a little over 1 standard deviation from the mean. And then in the range from 1 standard deviation, a little over 1 standard deviation to about 1.5 standard deviations, you see option 2 being a little bit preferred, being the highest probability, and option 3 being the highest probability. You'll also note that option 4 never is the most likely probability, ever, on any place of theta. And then finally, you'll see after you get about 1.5 logits above the mean, the most preferred response, the most likely preferred response would be the strongly agree option. So in looking at these plots, as the intercept changes, the location, sort of the peak of these curves change. And as the factor loading changes, or the discrimination, the steepness of these curves change. Similarly, to the binomial model, we can take a look at the item characteristic curves. Here we have item 10's expected value. Remember, our item numeric values range from 1 to 5. They're an arbitrary choice, but that's the range we have. The black dash blue lines here represent that 1 through 5, and you'll see the dash red line is our EAP estimated item characteristic curve for item 10, showing the expected value of the response. Right? The expected value for any given theta is the sum of all the probabilities above it times the value associated. So here you get 1 times this probability, you get 2 times this probability, and so forth, and you'd sum all those together. So this is our expected value right here. You can see that it takes somebody to be just about an average theta before they even have an expected value above 1. But if you want to look at where does somebody strongly disagree, it's a little bit before 1, and so forth. Once again, we can look at our EAP estimates of theta. Our distribution looks very similar to the ones we had before, although not identical. We can also look at 2 different posterior distributions of theta. This is person 1 and person 2. They're a little bit wiggly. I could have run the chain longer. That would probably smooth them out a bit. But for now, this seems to be okay. One thing I will note is it's hard to tell here, but the standard deviation, the posterior standard deviation, is different between these 2 thetas. And that's because, just like in the binary distribution models, the posterior standard deviation is related to the location of theta, sort of the mean of theta. And we can see that in this plot here. Here's our EAP estimate of theta on the x-axis. And on the y-axis is our standard deviation, our posterior standard deviation. As you can see, this range goes from about 0.6 to a little below 0.2. And in certain regions, we are much more precise with theta. Somewhere around between 0 and 1/2, we're pretty precise. And then a little bit closer to 1, we're a little bit more precise as well, too. If we were to compare our EAP estimates of theta from the graded response model with our sum score, remember the sum score is just the raw sum of item responses, this curve looks a little different than we saw in factor analysis, but very similar to what we saw in IRT and the binomial model in that it's curved, right? It never goes out of bounds because our model doesn't allow us to have, well, actually, sum scores can never go out of bounds, excuse me on that. But second, you'll see it has a little bit of an S shape to it, and that comes from us using this link function with theta involved in it. Similarly, we can compare our ordered logit model to our CFA model, right? This is our graded response. Theta EAP estimate is on the x-axis. CFA with a normal distribution for each item is shown on the y-axis. This is the EAP estimate of theta as well. And again here, because remember the normal distribution theta and the sum score are really highly correlated, so you can almost think that we'd get a very similar looking plot, and sure enough we do. But you'll see it's sort of it's still nonlinear in that the ordered logit has a little bit of a bend to it as you get up to the extremes based on the normal. Similarly, we can compare posterior standard deviations between the graded response model and the normal distribution. Here, our ordered logit from the graded response model these are posterior standard deviations on the x-axis, and these are posterior standard deviations of theta for the CFA model on the y-axis. You'll note the CFA model doesn't have a wide range of posterior standard deviations as we expected, but the ordered logit one does, and that's the interesting finding. The big pile of people who are down at 0, in particular, this pile right here, you can see them on the plot right here. They're those people right there. These people, you take a look at the difference. Basically, the lowest score we have based on our lowest EAP estimate of theta has a much larger standard deviation than what we would say in the factor analysis model. And again, this is caused by the nonlinearity induced with our distribution, the categorical distribution, and with our link function. So the next question is, which posterior standard deviation happens to be larger, the graded response model or CFA? And you can see that that pile of values were right. Actually, this is the difference between the CFA and the graded response model. You'll see that pile of people right here, much larger. You can also compare the values of theta between the binomial model and the graded response model. Remember, the binomial model was our previous lecture, and you'll see these are a lot more linear in nature, although they sort of curve toward the beginning, or the higher ends. And again, that's because in the binomial model, it assumes this symmetric binomial distribution. The places where the distributions are most different, though, tend to be in the higher parts of theta, and that's where you see this bend to it, whereas the graded response model provides for this category threshold parameter that allows us to have a differential shape to the distribution, which is, I believe, what you're kind of seeing from this point, from right about 1 standard deviation above. This sort of bends. We can also compare and contrast the graded response model posterior standard deviation, which is on the x-axis, and the binomial model posterior standard deviation of theta on the y-axis. And you'll see these are much more aligned than either of these were with the CFA model, because both of those are using categorical distributions. But in general, The ordered logit seems to have a bit more variability in there in the posterior standard deviation. And which one's larger? This is basically what you see. The standard deviation for binomial minus standard deviation for ordered. So anything positive here indicates when the binomial is larger. Anything negative indicates when the graded response model is positive. And you can see it's largely the binomial tends to be a little bit bigger standard deviation than the graded response model. So that's the graded response model. Let's push this one step further and go to the nominal response models, or the generalized logit models. Here again, we're going to use a multinomial distribution. We saw this slide before, so that means we're going to have a set of submodels, right? Because of our probability summing to 1, in our example, we have 5 categories. That means we can estimate 4 probabilities. The fifth one is just 1 minus the sum of the rest. But those 4 probabilities are now the basis of our submodels in our analysis. So the graded response model, actually, pardon me, in the graded response model, there's not 4 submodels, there's actually 5. Here, what we end up having is, in the nominal response model, pardon me on this, the nominal response model allows us to actually have 5 submodels here. However, there are some constraints that we need to identify the model itself. So what is the nominal response model? Here we're saying the probability y is equal to some category. Now I don't have equal to some category here, but that's what it should say. Conditional on your latent trait theta is equal to something that looks like the 2-parameter logistic model, right? We have a fraction where the numerator has the intercept for the item and category, right? With each category having its own intercept parameter. Then we have lambda, the factor loading or discrimination parameter for each item and category. And this is the big difference between graded response and nominal response. Here in the nominal response, we put no additional order constraint on the intercept, number 1. And number 2, we put no constraint at all, or actually estimate different factor loading or discrimination for each category. Now, there are some constraints to identify this. There are 2 options for the constraints. One is you can set the sum of each type of parameter equal to 0. Right? So the sum of all the mu's is 0, and the sum of all the lambdas is 0. Alternatively, you can fix one category's parameters to 0, right? So we could take arbitrarily the 5th category, set its mean to 0, set its lambdas to 0. When you do that, you'll see we get e to the 0th power, or 1, as a return. And that is one of the natures of this constraint. So why we have these constraints in nominal response is because we are estimating or trying to form each category's probability and to normalize it, so make it a distribution that sums to 1, we then divide by the total, right? So each category's exponentiated linear predictor summed together is our denominator here. And because this is the numerator for each category, and we sum across all the categories in the denominator, all of these now sum to 1. All these probabilities sum to 1, which is what we need it to be to make this a proper statistical distribution. All right, whew, so mouthful. How do we estimate this in STAN? How about we take a look at that next? Here in STAN, let's take a look at our item response. So now we have y for item and observation. Now this is a little bit different. Because of the way STAN works with vectors, I had to put now 2 loops in, whereas before I was able to vectorize this with 1. The 2 loops are a loop over items and a loop over observations. So here I'm looping over each item and each observation, and it turns out STAN has a nice function called the categorical logit that does the work for us. So what we do with the categorical logit basically is the following. We provide the linear predictor, and STAN will put in to the response the entire probability itself. So here our linear predictor I define as probvec, and I create that linear predictor. Probvec, by the way, has 1 probability for each category, right? Not each category minus 1, but each category. So I start off with probvec, and I tell it that each category I need to have its mean, and I need to have lambda for that category times theta. So this is my probvec vector. So here I form up each of the linear predictors. Once I have that, I put that into probvec, and I put that into the categorical logit function. And that ends up working out. Now, like when we went to the graded response model, we have multiple mu's, we have multiple lambdas, so we have to put both their hyperparameters in arrays. So you see both of these now are indexed by item. And within the items loop, we define them to have a multivariate normal prior distribution, as we've done for most of our parameters throughout class. We then provide a mean vector and covariance matrix for each, because there are multiple mu and multiple lambda parameters per item. Finally, we can have a theta distribution that's standard normal. And then I didn't mention this, but probvec I defined at the very beginning of the model statement as a vector, because I don't need probvec to be saved in my output. This is different than defining it in the parameter statement right here, where if I put probvec in here, it would save the values of probvec across the Markov chain, making my output extremely large. So our nominal response model parameters block. Now we have an array for our initial mu and an array for our initial lambda. Here, we'll note that this is a little bit different than we saw before, in that init mu and init lambda are the initial values. And this is because I have to make an additional constraint on mu and lambda. I'm going to set one of the mu's to 0 and one of the lambdas to 0. And so init mu and init lambda allow me to make the mean vector 4 elements, not 5. Because I don't need that fifth mean to have a prior, it's going to be fixed to 0. Same thing with the covariance matrix. If I didn't use this constraint, if I did a different constraint, here the covariance matrix needs to have 4 categories, not 5, because of our constraint. So we initialize these values as parameters right here, init mu, init lambda, and then we have theta. But you note that init mu and init lambda only have 4 categories for each item, or for each item, there's 4 values of mu and 4 values of lambda. Now, I have to introduce the transform parameters block to go and build stand code that will take the 4 values of init mu and the 4 values of init lambda and put them into a 5 category vector for each item, because the stand syntax expects us to have a mu and a lambda for each category, for all 5 categories. But I'm only estimating 4. So once again, I'm going to create init mu and init lambda with my estimated mu and lambda hyperparameters in these, or mu and lambda parameters in these values. And then in the transform parameters block, I'm going to move each value of init mu to mu itself. So basically what I'm doing is I'm setting category 1's intercept to 0 here with this line of code. That means category 2 through 5 take the value of my parameters right here, init mu. Same thing with lambda. I'm going to set the very first category's lambda to 0. And so the lambda 2 through 5 right here is the init lambda vector of our parameters. It's a little bit complicated, but transform parameters is a nice block. You use transform parameters to take parameters that you've defined, in this case init mu and init lambda, transform them, and then transform them, in this case to mu and lambda, in a place where you can use them in the model itself, right? The mu and lambda are in the model. You don't see init mu and init lambda except for in the prior statement here. All right, for the data step, as you would imagine, now we need multiple dimension arrays. Again, we have our imported max category. We have the number of items and number of observations here. We have a Y array, as we've seen before. Now, just like in the graded response model, though, for where we had 4 thresholds, here I'm going to import a mean vector of 4 hyperparameter means for each mu, and a 4x4 covariance matrix for each hyperparameter covariance matrix, for mu. But because each item has 4 mu's, and we need to make this an array. So the array itself for mean vector is item by 4 categories, number of items by 4 categories, or 10 by 4. And then there's a 3-dimensional array for the covariance matrix that's number of items by number of categories minus 1 by number of categories minus 1. So for each item, there's a 4 by 4 covariance matrix. And this whole syntax is repeated for mean lambda and cov lambda below. Both of those need the same array. In the same way of building data that we saw before, this is the same code that I gave you where I'm building in the array objects in R. The main thing to note is each of the mean vector and the covariance matrix are a matrix, a two-dimensional matrix for the mean vector, and a three-dimensional array for the covariance matrix. And we build our stand data with it. All right, here's our function call for this. Now you'll note I'm not initializing lambda. I'm not initializing lambda here because lambda can be negative in this model. In fact, there will be some lambdas, at least one lambda that's negative, if not more than lambdas are negative in this model. And that's because every category gets its own lambda, its own discrimination or threshold parameter. So if I started all the lambdas to be very positive, that wouldn't necessarily get me in the right spot. So here my initialization is just theta. I'm just going to initialize on the standardized sum score for theta here. So we run the model, and we see it converged. Hooray! Now let's take a look at our parameters. Now you may say, wait, why are all these zeros? Well, that's because, remember, our first mu parameter for our first submodel, we set to 0 to identify this. Then we get mean vectors, mean parameters for each of the other parts of our model, each of the other categories of our model. But these parameters are not strictly ordered. They may come out to be ordered, right? Let's take a look at item 1's set of mu's. We have 1.10 for mu 2, item for category 2, 9.70 for 3, 0.327 for 4, and negative 9.63 for 5. So these were ordered. It's possible they order themselves. But there are some cases it won't be ordered. So for instance, the mean parameter for the 10th item, the fourth category of the 10th item is negative 3.23, whereas the mean parameter for the fifth category of the 10th item is actually bigger than that, at negative 2.19. So you can see there's a whole bunch, these parameters are somewhat all over the place, but that's how the nominal response model tends to go. We have a similar feature for lambda. Now you'll note that the lambda parameters, though, are all positive. So it turns out why that is the case is, if you remember, our first category was the category where everybody was strongly disagree. So it's the most frequently picked category. Each of the other categories indicates a bit more agreement with the statement or the item, the question prompt. And so each of those represents a positive theta. So meaning that as theta goes up, the term multiplying them indicates a higher chance of picking those different categories. So that's what that represents. Now, what the parameters mean by themselves are somewhat hard to interpret because this sum at the bottom renders interpretation of these things to be very difficult. So instead, what we tend to do is build option characteristic curves, which I actually didn't do here. But to round this out, let's take a look at some of the comparisons here. Here is the comparison of the expected value of theta with the posterior standard deviation. This is our EAP theta versus the posterior standard deviation. Again, we have nonlinearity, but with the nominal response model, the most precise area happens to be a little bit less than 0 for theta, and you'll note that the value of the standard deviation is actually larger than it has been up to this point. Similarly, we have a theta estimate with our sum score. Now, these are not nearly as linear as you saw before. And again, that's part of the reason is because each of the items is being treated differently here. It's a bit more interesting. And if we compare normal versus, CFA is our y-axis, nominal response thetas, we have a similar plot to the sum scores. Remember, CFA sum scores are pretty similar to regular sum scores. And we can also compare our standard deviations. Again, the nominal response model is much larger for every standard deviation. And so you see none of these are bigger than 0. So the normal model always has smaller standard deviations. We can also compare thetas with the greater response model. And this is the part that's super interesting to me. What is going on over here? There's not really a trend, and that's because our nominal response model is this different class of model. It's not assuming ordered categories. So if for some reason our item responses somehow switch the ordering in the nominal response model in terms of what's more likely given theta, you may get a theta trend like this, where it doesn't quite map onto the graded response model. And similarly, we can take a look at posterior standard deviations for the graded response model and the nominal response model. And again, the nominal response model tends to be slightly larger, or perhaps even quite a bit larger here with the 0.6 for nominal response versus 0.2 for graded for this group. And which is bigger? Almost always the nominal response model has a bigger standard deviation. There's more parameters and it's harder to estimate, so that tends to give us a bigger standard deviation. So we could do this for any type of item, and I want to make this other point. Here we saw three different types of models. We saw a binomial only, where every item had a binomial distribution. We saw a graded response, where everybody had an ordered logistic distribution. And we saw a nominal response, where each item had a categorical logistic distribution, effectively, in the stand term for each of those. But there's nothing stopping us from mixing and matching. Remember, the likelihood, the the likelihood of the data, the model data likelihood, of y given theta is the product of each of the individual item response likelihoods right here. Well, it just so happens these likelihoods can come from any distribution. You could have some that's graded response and some that's nominal response, and it should work out just fine. So just a note, even though most of our examples in class tend to do what I'm doing here, which is all of one type, it's not necessary that you use all of one type. So that'll do it for this lecture. We had a lot more nominal response, polytomous data models. There's a whole bunch of them out there. This was sort of an introduction. Well, thank you for listening, and I hope this has been helpful in your Bayesian studies. Take care.